So in this talk, F will be a p-adic field of odd residual characteristic. G will be a connected reductive p-adic group. Let's see, the notation A sub G will be the denoting the maximal F split torus in the center of the group. Theta will be an involution of the group. H will be the fixed points of the involution. Okay, so we're going to be talking about H distinguished representations of G. So a smooth representation is H distinguished if the space of H invariant linear functionals on the space of the representation, let's call it pi v, is non-zero. Okay, so if we have a lambda that is H invariant, and we have a vector in V, then we can define a relative or generalized matrix coefficient. We evaluate the form lambda on pi of G inverse V. So this is our generalized matrix coefficient of pi. And an H distinguished representation is H relatively supercuspidal if all of its relative matrix coefficients are compactly supported modulo H times the center of the group. So every V lambda V is compactly supported. Notice that these functions are H invariant because of the H invariance of lambda, right? So they're really functions on cosets. Okay. Or let's say modulo H times the center of the group. So in this talk, we'll be describing some constructions of relatively supercuspidal representations. Okay, now it's known, actually, and some more background before I get into the construction. The following is the result of Cato and Takano, or separately Lagier. These were the people who introduced these notions in approximately 2008. An irreducible, H distinguished pi is either, and in order to not write too much, I'm just going to call this RSC for relatively supercuspidal. Okay, so it's either already relatively supercuspidal, or it can be obtained subquotient of something induced where P is a proper theta split parabolic subgroup and how is a relatively supercuspidal representation of a Levy subgroup. So here, theta split means P and theta of P are opposite. So this really is going to be a Levy factor of the parabolic. Okay? So this is a relative version of Jacquet's subrepresentation theorem. So it tells us that the relative supercuspidals are the basic building blocks for the distinguished representations. Okay, so there are some other facts about relative supercuspidals which may be mentioned later. Okay, so one fact that's already known, if pi is supercuspidal, and distinguished, then it's already relatively supercuspidal. So one approach to constructing relative supercuspidals is to simply go and look for distinguished supercuspidals. And this is also due to the people over there. Now, in general, if pi is supercuspidal, in this case, you can look at the form. So let's say, let's take a vector in the contragradient space, and then we're going to define a form by integrating the value of this form on a vector v is just going to be this integral Okay, so let's always assume, and I am going to assume that it's irreducible in general. So let's always assume that the central character is trivial here, H intersect the center. Without that, the representation can't be distinguished in the first place, so that's not actually a restriction. Okay, so because we're integrating matrix coefficients of supercuspidals, there's no problem with convergence here. Okay, and furthermore, the whole space is given in this way. Okay, so of course, if the representation is not distinguished, these forms are all zero. Okay, so in understanding supercuspidals that are distinguished, you need to understand enough about the supercuspidals to decide, when you get something non-zero here. Okay, so In joint work with Jeff Hakim, we describe the space of H invariant and functionals for pi tame supercuspidals. Okay, in order to have tame supercuspidals, we need to make an additional assumption though. So a tame supercuspidal is one of the supercuspidals constructed by JKU. Okay, so for this, we need to assume, and I'm going to assume this throughout the talk, that G splits over a tamely ramified extension. Of the field F. Okay, so this will be throughout the talk. Okay, so we did get a formula here, which I'm not actually going to take the time to just say a lot about. I will say a little bit about it when I need information. But sometimes we have a pair like this with no distinguished supercuspidals. E.g., the example of GL2N, SP2N is a well-known example of this. There are others as well. And even if there are distinguished supercuspidals, in general, what will happen is that there will be some relative supercuspidals that are not actually supercuspidal. So the goal here is to say something about what the non-supercuspidal relative supercuspidals look like. Okay. Another comment we can make in this vein before we move on to the general case is if G was something like restriction of scalars of a general linear group. Let's see, E tamely ramified over F. In this case, G has distinguished tame supercuspidals if and only if G contains tame theta split G regular elements. And this is actually an example where that would fit in this pattern here. So theta split just means it's mapped to its inverse under the involution. G regular, everyone knows what that means. Tame means belongs to a torus that splits over a tamely ramified extension. Okay? Pardon? H, and it's the fixed points of an involution. Any case like that, yeah.
What's theta here?
Pardon me?
I'm asking what is theta in this example? G equals 0, right?
Any involution. Yeah. It doesn't matter. Any involution. Okay, so the relative supercuspidals that we're going to look at are all going to have Tame support. Okay, so because we know something about distinction of Tame supercuspidals, we can apply that to the support, right? Okay, so now we're going to take a Levy subgroup. Okay, and then we're going to take a Tame supercuspidal representation. Okay, so the equivalence class of Cal corresponds to M equivalence class of a triple of the following form. Where M primed, pi primed, B. M primed is a tamely ramified elliptic twisted Levy subgroup of M. So twisted Levy subgroup means it's not actually a Levy subgroup, but it becomes a Levy subgroup over an extension. So M prime becomes a Levy subgroup of M. Actually, we should really talk about as an E group, right? Anyway, over some extension. And tamely ramified means the extension is tamely ramified. So tamely ramified extension, E of F. And elliptic just means it does not sit in any actual proper Levy subgroup. So M primed is not inside any proper Levy subgroup of M. So for an example, an elliptic maximal torus that splits over a tamely ramified extension, that's an example of an elliptic tamely ramified twisted Levy subgroup. Okay, and then the pi primed is just an irreducible depth zero, a depth zero representation, supercuspidal. So pi prime depth zero, irreducible, supercuspidal representation of M primed. And phi is a quasi-character of M primed. Satisfying some conditions. That is M factorizable and M regular on M prime 0 plus. So I'm actually not going to say what M factorizable actually is. It has a factorization somewhat along the lines of a Howe factorization, if you know about Howe's construction of tame supercuspidals. The regular condition is a little easier to describe, and essentially what this means is that when you take phi and you restrict it to here, it could not be equal to, let's say, some other quasi-character restricted to there, where chi is a quasi-character of, let's say, M double primed with M prime contained but not equal to M double primed. And this is another twisted Levy subgroup. So it can't come by restriction from a larger twisted Levy subgroup. That's the regularity condition. Okay. Now this is basically more or less, it is a consequence of the work with Jeff Hakim mentioned above. And originally this was proved subject to some hypotheses. So originally subject to hypotheses concerning properties of quasi-characters of twisted Levy subgroups. Actually, but if the group was GLN, then actually there were it was automatic. But for other groups, there were possibly some hypotheses. But recent work of Tasho Kaletha removes these hypotheses. So we only need p-odd here. That's it. So. Okay, hypotheses. Yeah. Okay, so this is just some background on equivalence classes of tame supercuspidals, but I'm just stating it relative to the Levy subgroup because actually I'm going to use it on the Levy subgroup. The equivalence relation is the obvious one. Yes, so it's basically conjugation and equivalence, right? So we obviously can just take that tensor of pi primed and phi because phi is a quasi-character of m primed, right? So you take the representation pi prime phi, that representation of m primed, and if you have another triple, it's equivalent if you can conjugate the one to the other. Right? So it's the obvious notion of equivalence. I'm not going to write it on the board. Okay. Okay, so the idea is to choose particular Levy subgroups and then choose some particular tame supercuspidals on those Levy subgroups and impose some conditions which will guarantee that when we do parabolic induction, we produce some relative supercuspidals. Okay, so I'm going to try and describe something about how that works. It is rather technical. So I'm only going to give a general idea of what's going on here. Okay, so so here's the theorem. This theorem does not say anything about relative supercuspidals, but it is used in the proving that certain representations are relatively supercuspidal. So here, I need to assume I have to be careful about the residual characteristic, so I actually don't really want to say in what ways I have to be careful. So as long as P does not belong to a certain finite set, so P is the residual characteristic. Depending on G or its root datum, actually, really, P should not be a torsion prime for the dual of the root datum, but I think we have some other constraints as well. And pi is an irreducible H-distinguished tame representation of G. So a tame representation of G means the obvious thing. Cuspidal support is tame. Okay, so that's what I mean by a tame representation. Then actually it's inertial support. Is H-distinguished. And what I mean by that is that the inertial support consists of, obviously, it's only really defined up to conjugacy and equivalence and twisting by unramified quasi-characters. But there is so inside the inertial support, a pair, right? This is like the cuspidal support, except you allow unramified twists, right? Inside here, there exists something like that where M is theta stable, and tau is M theta distinguished. That's what distinction of the inertial support means. Okay, this was done in Depth Zero already, published in Journal of Number Theory, 2015. And actually, for the depth zero case, I don't need any constraints on P, except p-odd. But for positive depth, I do need some. And now the general, it's actually in preparation. Okay. So I'm going to make a few general remarks about the proof. Okay, so I would take remarks about the proof, but they're really general. So let's take. Okay, I'm just going to take it in. It doesn't really matter. Here. Okay, so it's tame by assumption. So we know it's induced somehow. Compact induction, right? Say something like that. J is open subgroup, compact mod center of M. Okay, and then let's look at the intersection of all the kernels of the unramified quasi-characters of M. And then we'll take the intersection here. So we want to move down to an actual type. So we want to move down to a compact subgroup. So we're just going to take the maximal compact subgroup inside the inducing subgroup. And rho M, irreducible constituent of the restriction. What was it? Kappa. Okay, so kappa restricted to Km. Okay, so in this case, this pair is a type in the sense of Bushnell and Kutsko. Okay. And it actually determines the Bernstein component, a particular Bernstein component in the decomposition of the category of smooth representations of M, because this type is very large. Normally, a type will actually give you something involving finitely many decomposition with finitely many inertial classes, but if the type is large enough, it will actually involve one particular inertial class, and that is, of course, the inertial class of the original tau. Okay. All right, so one key thing is just to make sure that all the types we take are actually large enough in some sense.
Can I ask one question?
Yes?
You mentioned previously that every distinguishing used from this relatively, or whatever it's called. Previously, the statement was that every distinguished is induced from this relative supercuspidal. But now it's discussed, you know?
Yes, so I'm putting the cuspidal on the levy, and then I'm going to induce. Right?
Right, but you attributed the result to 2008.
Yes, so the point is that we do not actually know what the relative supercuspidals are, right? And so we want to say, how do we get the relative supercuspidals in the first place? So it's enough to describe how to get the relative supercuspidals for G, right? Then you'll know how to get them for any levy. So the point is to produce the relative supercuspidals first, and then if you wanted, once you have them, you start doing this induction and decomposing. Right? Yeah. Okay, so now construct a G cover K rho of this representation here. Okay, so normally this is one way to produce a type at the level of G, is to have a type at the level of a levy subgroup and then construct a G cover. Again, in the sense of Bushnell and Kutsko. These notions were all described by Bushnell and Kutsko. So how do we do this? Well, because of, what we do is we apply results of Julie Kim and JKU, where actually what they do is they construct G covers of types that occur in tame supercuspidals. Okay, so I'm just using their types here. Okay. And in this case, because the type, again, because the type is large enough, this type, K rho, actually determines the Bernstein component associated to this inertial equivalence here is the inertial equivalence class of the pair, of this pair. Okay, so in the category of smooth representations. All right, this is just the Bernstein component. Okay. Okay, so now we actually really want to study distinction here, right? So what we're aiming for is this distinction of something in this inertial class here, right? So somehow we have to figure out that, at least at first, that some conjugate of m would even be theta stable in the first place, and then also that the corresponding tau would be distinguished there. So the general form of K rho has similar properties to K m rho m, except at the level of the group G in particular. So in the case of the cuspidal case here, you have a cuspidal m datum here that appears in U's construction. And here you have a cuspidal a non-cuspidal, just a G datum. There's a notion of G datum here. Okay, so in order to define the G datum, it's actually more involved than what happens in the supercuspidal case, even though it has some similar sort of properties. And part of the issue here is that we have to be very careful. When we work in the supercuspidal case, we actually end up with various twisted Levy subgroups that happen to be elliptic, say in M, and then we embed the building of these twisted Levy subgroups in the building of M, sorry. But in some way, because of the fact that the twisted Levy subgroups are elliptic, it doesn't really matter what kind of embedding you actually use. But when we move up to G here, now our twisted Levy subgroups, whatever they might be, what they are is they're twisted Levy subgroups that come up in some sort of factorization of phi, but a G factorization of phi. So what I am also going to assume is I'm going to assume here that phi is G factorizable. And again, this is almost always true anyhow, but I will actually say this explicitly. Because we need this in order to define this cover and to define this G datum. Okay, now it is very technical, and that's why I'm not saying much more about it. But it has enough similarities to the cuspidal M data that we worked with before when we were studying distinguished supercuspidals. So we can use some methods that are somewhat similar to study distinction. So if we look at the representations that we're interested in, say we're interested in the representations whose inertial support is this, they're all going to contain this type. In particular, they're not just going to contain this type, they're actually, the isotypic space for this type is going to generate the whole space of the representation. So what that means is that if the representation is distinguished, then when we conjugate this around, there must be a conjugate of this that is basically, there exists G and G, such that when we look at the intersection, this better be non-zero if the representation is already distinguished, which we assumed it was. Okay, so we can start looking at what's happening here at the level of this finite dimensional representation. And we can argue in a way that's somewhat similar to what in the supercuspidal case, and we can obtain some results about behavior of these types relative to the involution theta. So we obtain results about, I'll call it theta symmetry of some conjugate like this. And then because it doesn't actually matter which conjugate we took, we'll just remove the G and assume we had something that had symmetry properties. So this is not quite enough to get the theorem, but because this pair is actually a G cover of the original representation, that's not quite enough to get that M is theta stable. So even if we have, say, okay, after conjugating, we just have this thing, right? We'll replace it. The symmetry by itself is not enough to make the M theta stable because there's some issue with depth zero types. In the supercuspidal case, we can always reduce to, when we do these symmetry results, we reduce to a cuspidal representation over the finite field because we have some sort of maximal paraphoric involved. But here, we only get to something that's depth zero. So in order to complete the proof, we use the result about depth zero. So, and then to complete the proof, apply the results, the depth zero results. Roughly speaking, this is how it goes. So we need to understand the depth zero stuff first. And actually, I'm really glossing over a lot here. It's actually not just depth zero distinction, it's really depth zero distinction, quadratic distinction, because when we do this sort of argument and we study these spaces, when we reduce to depth zero, we actually get quadratic distinction at depth zero as opposed to distinction. But that, I think for getting an overview, you don't need to know too many details about that. So in the end, we actually do get what we want. We actually do get that the inertial support is actually distinguished. It's very much an argument involving types, though. Everything is about types and analyzing the behavior of types relative to the involution theta. And so if you look at this construction, a lot of it involves the building on the Bucharditz theory, because that's how the JKU's construction actually works. It involves that kind of thing. Okay, so that's just some general comments about the proof. And in fact, this theorem is a key part of what we do, applying this theorem. Okay, so now some more. Okay. So looking at what we have over there, going back to the supercuspidal and the triple that determines the supercuspidal, in an M factorization of phi, a sequence of twisted Levy subgroups of M appears. Each of these is elliptic in M. Okay, so elliptic twisted Levy subgroups are key in the construction of tame supercuspidals. We just happen to be doing this on a Levy subgroup. So now what we're going to actually do is we're actually going to make a definition, a twisted Levy subgroup of G is relatively elliptic or if you want to really specify that it's theta, you could say theta elliptic. If let's call it G primed. So we have a twisted Levy subgroup G primed of G. It's relatively elliptic if it doesn't sit inside any proper theta split parabolic. Okay. Not inside a proper theta split parabolic. Or equivalently, if we take AG primed minus, it's actually AG minus. So here, these are maximal, F maximal, theta split tori in AG primed. And oops, theta of G primed equals G primed. And it should be theta stable to start with. We only have to consider theta stable twisted levies. So this is a maximal theta split tori, so torus in AG prime and AG, respectively. Okay, so theta split torus is a torus in which every element is theta split. Okay, so this is when I'm defining a relatively elliptic, and it turns out that the relatively elliptic twisted Levy subgroups are the ones that are important for relative supercuspidals. Okay, and it really is a direct analog, right? The elliptic ones are the ones that don't sit inside proper levies, and the relatively elliptic ones are the ones that are theta stable and don't sit inside any proper theta split parabolic. Okay, so now what I'm going to do with the construction is now I'm going to actually assume that my M is relatively elliptic. So now, without loss of generality, we certainly know that theta of M equals M. By the theorem that I've just erased, we can assume that we've got something in our inertial support that's already distinguished, right? So theta of M equals M. So let's assume it's relatively elliptic. And actually, the other things that we can assume are, we can also assume that we have some symmetry at the level of the character, at least on topologically, oh, actually, we can also assume M prime is theta stable. Okay, so the 0 plus always denotes the topologically unipotent set. Yeah. Okay, so we can make all these assumptions because these things come out of the proof where you prove that the inertial support is distinguished, right? And so the extra assumption I'm making here is just that this is relatively elliptic, all right? Then every parabolic with Levy factor M is theta stable. So in particular, pH is closed, right? So if we have an invariant form at the level of the Levy, or up to some sort of twist, then we're going to be able to lift it to an invariant form at the level of G, okay? We don't really need relatively elliptic for this. This will work if the parabolic's theta stable, but we need relatively elliptic for other things here. Okay, so what we have is what we need to have if we want, oh, and also this thing, theta fixed point is a parabolic subgroup of H. So putting the modular functions in, because we're going to do everything is normalized. If this is not 0, then we can take a lambda in here and lift it to here just by doing integral with respect to some quasi-invariant measure, right? And this is the same, by the way, if tau is one of our Tame supercuspidals. This is actually the same as a particular for a particular unramified twist. So tau. So it really is the the inertial support is distinguished there. So so we do this, and then we decide, okay, so now we're going to induce, and it's H distinguished. And the goal is to see when is it actually relatively supercuspidal. Okay, so when is pi, and it's irreducible subquotients relatively supercuspidal. Okay, well, we know, okay, so it's not always going to be the case. So some conditions need to be imposed in order to guarantee that what you get is relatively supercuspidal. And I'm going to try and say something about those conditions. Okay, so going back to the comments about factorizability here and regularity. So this phi that we had was regular with respect to M in some sense. You cannot get it from a quasi-character of a strictly larger twisted Levy subgroup. Okay, but it's not necessarily G regular, right? So phi is not necessarily G regular. Okay, so we're going to choose a twisted Levy subgroup. Oh, and I should also, yeah, whatever. Choose a twisted Levy subgroup G prime of G. Okay, so we've got our, M is in M primed, I guess. Do I really care? No, M primed is in G primed, is in G. Minimal with respect to the way we get phi on M prime 0 plus is by restricting something from G prime 0 plus chi quasi-character of G primed. Okay. M primed is actually going to be a Levy subgroup of G primed. Also, G prime is going to be theta stable. Okay, so minimal. I want it to be the. I guess maximal. Sorry. Yeah. Yes, I want it to be the maximal. Thank you. Yes, maximal with respect to. Yeah. So erase that and change it to maximal, because I'm not going to get that board back down here and do it. So. Okay. Yeah. Thank you. Okay. So it's theta stable. And so one thing that we can say, there's several things where things get a little involved here. So here's one result. If every theta split element in the normalizer of M primed and G primed is in M primed. So remember that theta split just means something that gets taken to its inverse under theta, right? If all of the theta split elements in here are actually in M prime, then pi and all of its H distinguished subquotients are relatively supercuspidal. And from what I'm going to say in a moment, maybe it'll become clearer what's going on here. And then there's going to be another thing we can say. Just let me. Okay, so just a remark before that will make things a bit clearer. If we look at the following, suppose the following is true. Suppose that for every Q plus LU proper theta split parabolic, where L is the natural torus of Levy here, there is no irreducible subquotient of the Jacquet module. Some people write it like this, and some people write it like this. That is distinguished. Right? Under these circumstances, the representation has to be relatively supercuspidal, because there's a theorem that I haven't mentioned. I'm really out of time, but we actually have a way to descend form. So suppose we have a form like this. And then there's this work of Cato, Takano, and Lagier. You can actually descend to a form, let's call it lambda u. Like this. And there's a characterization of relative supercuspidals that's analogous to the characterization of supercuspidals. You know, a supercuspidal is a representation of supercuspidal if and only if all of its Jacquet modules are 0. So a representation, an irreducible representation that's distinguished already, is relatively supercuspidal if and only if all of these forms are 0. Right? So pi RSC if and only if lambda u equals 0 all lambda here. So this is actually what we're doing. The result on distinction of inertial support is key for doing this, to actually show that no irreducible, you see, you can't use the geometric lemma, because the geometric lemma will only help you with the actual JK module or quotients of it, right? If you're interested in subquotients of it, you have to just use inertial support. So, and properties of inertial support. So this is what we're actually doing here, and this, although it's not obvious why, it actually guarantees that. So this is one condition, but it's not as general as it should be. So what happens in general is, well, actually, so what you need to do, so you actually show, given the symmetry conditions we already have on the M, if G is in G, GM is theta stable, and GM happens to get inside one of these levies, then when you look at distinction relative to theta of the original representation conjugated by G, twisted by something unramified, I don't really, this doesn't matter here, this unramified thing, is 0. And actually the chi is irrelevant because we're doing it at the level of types. Yes. That's actually what we show. And then we use properties of inertial support. And that will tell us right away that this is happening when all these forms are vanishing. We don't actually, in general, know a lot about these forms, but if there's no distinction, then there's no non-zero form, right? So basically, this is what we have to do. And if you think about what it means for this to be theta stable, when M is already theta stable, what it actually means is G inverse theta of G is in the normalizer of M. Here's an element that's theta split, and it's in the normalizer of M. Okay, so when you look at this condition here, why the G primed and the M primed are appearing here is because all of these arguments involve a reduction to depth 0. So we first start with our Levy subgroup M inside our group G. But when we look at the distinction, we can always reduce to some sort of quadratic distinction for types, depth 0 types, at the level of the groups M primed and G primed. And so that's where this is coming from. It's actually related to this condition, but I'm not describing exactly how it's related to this condition because I'm not describing how one does the reduction to depth 0, right? But if this is what this is coming from. Okay, so now, this is something that does sometimes happen. So this is an easy thing usually to verify in examples. So you can construct a lot of relatively supercuspidal representations using this criterion. But we actually want something general. We want something that's as general as it possibly could be. So what's happening here is you're basically ruling out the complications with theta split parabolic subgroups inside G primed by imposing this condition. So there's lots of examples also don't have this happening. So what happens in general, and I'll just make a few remarks on one of the sideboards here because there isn't time to really explain it. There's actually not time to explain much of anything here because it is rather technical. But what happens is, in general, so we have the G and the M, and then we're reduced to depth 0 in some way. And what should happen in general, we get some sort of criterion for relative supercuspidal of some depth 0 types. relative cuspidal criterion for depth zero types arising here. Actually, depth zero types, for quadratically distinguished. Depth zero types. Arising from our types that we had, right? Remember we had this type, and then we had this type. And each of these has a depth zero piece to it. And we have to take a depth zero, we have to modify things, and we take the depth zero piece of this and we make some changes to it. And then we take the depth zero piece of this, and we end up with some sort of parabolic induction over the finite field. And the relevant parabolics over the finite field actually is also relatively elliptic. And you get down to some sort of relative cuspidal property for depth zero types. So that's actually what you would expect if you know how Yu's construction works. He has some conditions on some quasi-characters, and then he has this cuspidal condition at the depth zero piece. So here, we have conditions on our quasi-characters, and then we should have, for some particular choice of depth zero type, a relative cuspidal criterion for that particular choice of depth zero type. Now, I'm not stating this as a theorem because I haven't checked all the details yet, and therefore I would not feel happy about doing that. But I actually think it does work. In any case, I haven't even said what the criterion is, so you have nothing to actually decide whether or not you believe what I'm saying. But it really does seem to work. And this should be quite general. What we don't have, and I'm wrapping it up, it's okay. We don't have any sort of exhaustion result yet, because we don't know how to show that what we're getting is everything. When we do this, I've shown that every distinguished subquotient is actually relatively supercuspidal. And I know there's a distinguished quotient, but I have no idea what other subquotients might be distinguished. I also don't have a multiplicity formula, except in some special cases where things look really easy and I can actually write down a multiplicity formula. So there are some cases where you have these representations are associated to some very nice, basically the depth zero part is trivial, and there's some really nice theta stable torus and a quasi-character of a torus that gives us our representation. So there are some nice cases which are much simpler, which you actually might have been happier if I talked about those. But anyway, I really wanted to say something about the general setup here. So this is sort of a state of affairs with general construction of relative supercuspidals, but only in the Tame case. Thank you.